Hi gang, video for today. Now that we've covered oxidation numbers and how to figure that out, we can utilize that for really the key for most of this chapter is how do we name something. That's kind of important because if we don't speak the same language, problems happen, right? You're talking to, if your pharmacist is talking a different language than you, and you say you need this, but they read things differently than you do, and you're both correct. If you're using your own system, you both think you're right, but you think each other is wrong. You might get the wrong medication, right? Bad things happen. Very critical that in the science community, we agree on our language that we're using. Otherwise, it's a nightmare trying to figure things out. All right. And this has been, I'm not going to go deep into the history of nomenclature, but it was a little ugly in the past, right? We're all like, oh, what do we do? Trying to figure things out. Things are a process and things adapt and change over time. So we're going to build our way up to the system. We're only going to use one system in this class, right? But I want to introduce you to some of the other systems because sometimes history lingers a little. All right. Before we had any kind of international scientific community, pretty much people fended for themselves. So we had what was called the common system or common names. You'll hear people call those different things. The only thing that really lingers from there is water, right? Imagine if you didn't know what water was and you're trying to figure out the chemical formula. Somebody says, hey, write the chemical formula for water. You're like, I don't even know what elements are in it. It tells me nothing. Absolutely zip. You have to memorize what it is. And that's what the old common system was back in the day. It was brutally difficult. How are you supposed to know saltpeter is potassium nitrate, right? KNO3. We call it potassium nitrate now. And you could figure that out, potassium and nitrate. Oh, right? But how would you know saltpeter is KNO3 unless you memorized it? And some things still linger. Lime. Right, in the limelight, on stage you're in the limelight. So lime was a common name for a calcium-based compound back in the day. All right, so we're just gonna sweep that one under the table, and water will be the only one that we will still use, even though it's technically incorrect, right? But you don't want to look like a weirdo going into a restaurant. May I have some dihydrogen monoxide, please? And those, the waiter or waitress would look at you like, what are you snorting? Okay, but they know what water is. You see what I'm saying? And then it advanced to a valiant attempt at naming things. Specifically, this is for ionic compounds with some of these type 2 metals that can form multiple charges. Well, how do you know, right? You just can't say, can I have some iron sulfide? Because iron could be a +2 or a +3. So how do you know which one to bring somebody, right? Say you're working for some scientist or something, and they, hey, I need some iron oxide or iron sulfide. You're like, I don't know. You see, which one do I bring you? So we need some way to clarify which charge. Right? Is it the iron sulfide with the iron 2, or is it iron sulfide with the iron 3? How do you discern between the two? Well, we have a better system now, but back in the day, a lot of people spoke Latin, right? So that kind of lingered up until the 60s and 70s and early 80s and has slowly been phased away by the new system we're going to learn on the next board. But in the Latin system, I'm not going to test you on this. You'll never see it on my exams or quizzes, but it may pop up if you're reading some older literature and whatnot. Anything that has a Latin root, like tin, those kinds of, where does SN come from in tin, right? Or lead, PB. Well, it comes from Latin roots, just like iron, Fe. So what you do is you take the Latin root for, right, fair, right, or plum for lead, or stan for tin. Take the Latin root and then add a suffix to it that designates which charge it is, right? If it's the lower of the two charges, we give it an OUS suffix. If it is the higher of the charges, it gets the IC suffix. So this would be ferrous, or the ferrous ion. Today we call it the iron 2 ion. That's a lot easier. This would be the ferric, or ferric ion, but we call that iron 3 today. So at least you got an idea of what pain we had to go through before. Nomenclature is going to take a while, so this will probably break up into 2 videos. We'll start with the ionic compounds. Let me show you the system that we're going to be using, the International Union of Pure and Applied Chemistry, or IUPAC. That's our baby right there. And we're not going to be naming organic compounds. The naming system we're going to be using, again, is the IUPAC, or International Union. International Union of Pure and Applied Chemistry, fairly recent in modern history. Can't remember the exact date. I think it's the 60s or something. Don't quote me on that one. But we finally got an agreement in the science community to use the same thing across the planet. It's fantastic. All right, so I'm going to go through the rules based on the type of compound. So, and again, organic chemistry has different rules. Complex ions have different rules. Specifically, just our general chemistry, inorganic compounds. That's what we're going to look at. I'm going to break it up into 3 categories, and each has subtypes. Under ionic compounds, we're going to have a particular set of fundamental rules. But we're going to deal with ionic compounds that have type 1 metals, type 2 metals, which can vary, so we need to twist the rules a little bit to account for the fact that metals can have multiple charges for type 2 metals. And then what if we have polyatomic ions in there, right? So how does that alter the naming system? But they're all kind of similar. We're going to look at covalent compounds, which are nonmetals with nonmetals. And we're going to see that those have slightly similar rules to ionic, but just with a little twist because they're covalent versus ionic. And then we're going to look at acids. Acids usually cause the most trouble for people. We're going to look at 3 different kinds of acids. We're going to look at what are called pure acids, which you probably didn't look at in introductory or high school chemistry, would be my guess. Pure meaning it's in its pure state, liquid, gas, solid, that kind of thing. What if we dissolve the acid in water? This is by far the most common you'll run into, right? You know, you find a solution of hydrochloric acid. You don't find HCl, you know, in the gas phase or something, right? That'd be nasty. So we're gonna name solutions of acids versus pure acids slightly different. And then oxy or oxo acids, which we'll find out are where the acidic hydrogen is bound to an oxygen in a polyatomic ion, like your HNO3, H3PO4, those kinds of things. And we'll look at terms called binary versus non-binary. Binary has 2 different elements. Non-binary could have 3 or more, like NaCl, that's got sodium and chlorine, that's binary. Whereas HNO3 has hydrogen, nitrogen, and oxygen. That's not binary, right? It's got 3 different elements. We'll go through each category, and when we're all done, we'll summarize it all on a nice little flow chart, which is in your general, if you're in my class, your general chemistry notes, page 92, right? I think I got that wrong. The oxidation numbers in the last video, I think I said 92, that was 96 or something like that. But you can, that's what an index is for, you can find it. But if you're in my class, I kind of typed up a nice little summary table. So we're going to have 1, 2, 3, 4, 5, 6, 7 different categories of compounds. 1, 2, 3, 4, 5, 6, 7. Similar naming, but with slight little twists and turns. So let's start with ionic compounds and see how long this video goes. If it goes too long, we'll do the covalent compounds and acids in a second video. Here we go, my friends. Let's start with the easiest, gang. You already know how to do this. I'm sure you do. So type 1 ionic compounds. And this is going to be our basic framework for naming most of our compounds. All we're going to do is just add a little fine-tuning to it. So again, a type 1 ionic compound, specifically we're going to do binary ones. So there's only 2 elements. You've got a metal cation and a non-metal anion, right? Monatomic. It's a type 1 ionic compound because it contains a type 1 metal. Remember, we got type 1 and type 2 metals. Remember, those are the group 1A, the alkali metals, group 2A, alkaline earth metals, aluminum, silver, cadmium, and zinc. We can assign those cation charges based on the periodic table. They only have that one value naturally, which is nice because we don't need to designate the charge of that metal cation in the name because it only has one charge. So it's redundant to put it in the name. You agree? So we're going to always name the metal cation first. And remember, metal cations retain the original name. So sodium ion is sodium, barium ion is barium, so on and so forth. Name the non-metal anion second. Remember, we take the root, like for chlorine, you take the root chlor and add the suffix IDE, chloride. So this is your prototypical way of naming things. So for example, let's do a couple. Go ahead and name that one for me real quick. And then we'll do that one. See how they're binary? Only 2 different elements, metal, non-metal, right? So if I'm going to do this, I'm going to name the cation first, and I know magnesium is a +2 because it's an alkaline earth metal, but I don't have to put the +2 in the name. So it just retains the original name. So that's just magnesium. And then look at the anion. So that's bromine, but as an anion, Br-, that's bromide. Take the root plus the suffix IDE. And there you go, magnesium bromide. Oh, these are the easiest. Here, now silver, even though it's a transition metal, it is one of the type 1s because silver is always a +1 charge. That's why there's 2 of them with the sulfide, the -2. So the silver just maintains the name silver. That's the name of one of my cats, by the way. I have a plethora of kitty cats. And sulfur, take the sulf, add the suffix IDE, so silver sulfide. I could go on and on and on, all right? So there's, look for any worksheets you have. I know for my class in the general chemistry notebook, we got 2 pages of worksheets on nomenclature. Yay! We'll probably have some in lab. We're going to be dealing with lots of homework. I have practice examples on my web page. You want to get really good at it, and it's just by doing it over and over and recognizing really it comes down to what class of compound is this? Which of the 7 possibilities? Is it ionic? If it is it type 1, type 2, or polyatomic? Is it an acid? If it is it a pure acid? Is it an aqueous solution acid or an oxy acid? Or is it a covalent compound? Because each one has a specific twist to its naming rules. So if you're not familiar with it, you'll name something with the wrong set of rules. I see it all the time. Let's do type 2 ionic compounds in case we have a type 2 metal in it. We're going to do the exact same thing, just to add one little thing to it. Type 2 ionic compounds, I think, are almost just as easy as type 1. It's just you got to figure out the charge of the metal. So again, type 2 ionic compounds, and we're doing binary ones only. So you got a monatomic metal cation and a monatomic non-metal anion. We'll do polyatomic ions later. So that metal cation is type 2. So anything that's not group 1A, group 2A, aluminum, silver, cadmium, or zinc. That's because they have more than one possible charge. Sometimes, at least 2, sometimes 3, 4, 5 different possibilities. How do you know which one? It was like I was talking about earlier. Yeah, go get me some iron sulfide. Which one? Iron can be +2 or +3. And back in the day, they'd say ferrous sulfide or ferric sulfide. But we're going to use the International Union of Pure and Applied Chemistry. So we'll just call it iron 2 or iron 3. So we're going to designate the charge of the type 2 metal using Roman numerals. History can't escape it. In parentheses after the cation name. So if I say iron, I'm going to say iron parentheses 2, Roman numerals 2, or iron parentheses 3, Roman numeral 3, to designate iron 2 sulfide or iron 3 sulfide. Right? And back in the day, they called it ferrous sulfide or ferric sulfide. So the extra step to this is looking at the formula unit of the chemical formula of the compound and being able to look at it and hopefully in your head be able to go, I can reverse engineer and figure out the oxidation number or the charge of that metal in my mind. If you can't, just set up the algebraic expression and solve for it. So it's kind of a part A, part B. Solve for the charge of the type 2 metal, boom, and then insert that into the name. Let's do a couple examples. I'll erase the board and see if you can do them. All right, pause it. See if you can name these 2 ionic compounds. How do you know they're ionic? Metal, you got the metal cation, non-metal anion, metal cation, non-metal anion, binary, only 2 elements. Got to recognize SN is tin. That's not a type 1 metal. So this is a type 2 metal. So we got to figure out its charge first. And cerium, I think it's one of the lanthanides or something. That's not a type 1 metal either, so we don't know what its charge is. We're going to have to figure it out. So let's do oxidation numbers first and figure out the charges of these. So we're going to assign fluorine a -1, and we don't know the tin, correct? Over here, we don't know the metal, but we always know the non-metal. We know sulfide is always a -2, but we don't know the cerium. All right, so let's set it up. We can do this. So for the tin, we've got 1 tin at X plus the 4 fluorides at -1 equals 0. So X equals +4. So the tin is a +4 in that one. Here we've got cerium. We've got 2 of them. Let's call that X. Right? So let's go X and X. Let's add the 3 sulfides at -2. That will also equal 0 because they're always going to equal 0. These are ionic compounds. So move the 6 over, so 2x equals +6, so x is +3. So that's the first step. If you can do that in your head, more power to you, my friends. You don't have to show me all this garbage, right? Now we can name it. Yay. Let's do that in brown. So many color choices. We're going to name this as tin fluoride, just like type 1, but we're going to add the charge in Roman numerals. So we're going to go tin. Hopefully you know your Roman numerals up to 10. Tin 4 fluoride. Right? You can't say tin fluoride because tin can actually be a +2 or a +4. Now back in the old days, they would have called this, if tin can be 2 or 4, the Latin root is stan, so tin 2 would be stannus, tan 4 would be stannic, this would be stannic fluoride. I'm never going to test you on the Latin system, my friends, but you may run into it. See how much nicer the IUPAC system is than the Latin? The Latin system, which I tail-ended in my college days, you had to memorize all the Latin roots, all the possible charges, right? You had to know what the lower and the higher charge. Oh, man, it sucked. All right, here we've got cerium. What's the charge on the cerium? 3, we've got included because it's type 2. Put the Roman numerals of a 3 there, and then add the anion, where you take the root plus the suffix IDE. So that is cerium 3 sulfide. Not too bad, especially if you can do that in your head real quick. Just go, oh, that's a +3, that's a +4. If you can see that real quick without doing the algebra, just pop it in the name. Piece of cake, my friends. Make sure you practice these. So let's do ionic compounds that contain polyatomic ions, and we're going to find that we do it exactly the same way. It's not really a separate category. It's not a binary. If you have a polyatomic ion as your anion and a metal as your cation, you're going to have at least 3 different elements, so it's no longer binary. But we're going to use the same rules for type 1 and type 2 ionic compounds, right? If your metal, because the polyatomic ion has nothing to do with the metal. So if the metal's type 1, you don't need the charges in Roman numerals. If it's type 2, you do. So we'll treat them just like this. But we're going to name the anion slightly differently. We're just going to stick in the name of the polyatomic ions. Pretty easy. So for ionic compounds that contain polyatomic ions, again, they're no longer binary. No longer binary. That's how you recognize them. Don't freak out. Just name them exactly like we did type 1 or type 2. So look, recognize the metal. Is it type 1 metal or type 2 metal? Name the metals exactly the same way. And then add the polyatomic ion, which most of the time will be your anion. And just stick that in. You don't alter it at all. Nitrates, nitrate. Phosphates, phosphates. Carbonates, carbonates. Dichromates, dichromate. You just stick it on there. Bloop! You're good to go. And if it's a type 2 metal, add the charge in parentheses as Roman numerals. You're off to the races. If it's a cation that's got a positive charge, like the ammonium ion or something, you just stick an ammonium there. Then you don't have to worry about the type 1, type 2 metals. Let's stick a couple examples up on the board, and we'll be done with ionic compounds. Here's a couple examples for you. See if you can pause the video and name those for me. Obviously, you can tell they're not binary, right? We've got lead, hydrogen, carbon, oxygen. We got 4 different elements in there. That's not binary. And here we've got nitrogen, hydrogen, phosphorus, oxygen. That's not binary either. We can do it. Let's take a look. Do you recognize, you see the parentheses there? That's usually a big indicator you've got a polyatomic ion. And we've got lead, and lead's not a type 1 metal. It's type 2, so we're going to have to figure out the charge with the lead. Now, we can kind of do a shortcut. You don't have to assign, one for that, and you don't have to assign all the individuals. You can see if you've memorized, like I recommended, the polyatomic ions, you know that is HCO3-. You should know that. It's going to make your life much less miserable, all right? We know the bicarbonate or hydrogen carbonate. Yeah, old way was bicarbonate. It's still hard to get that out of my brain, but it technically should be hydrogen carbonate. We know that's a -1. And there's 2 of them, correct? And there's only 1 lead, so the lead must be +2, or back in the old day, plumus. Lead 2 is plumus, lead 4 is plumic. we can do this. Let's name this baby. Let's do it in brown. So that's type 2 metal, so I got to put the lead. Let's put the charge in Roman numerals, just like we would for any type 2 ionic compound. And then all we do is just add the name of that polyatomic ion, because the charge doesn't change, so we don't alter anything. So lead 2, hydrogen carbonate, or you could go lead 2 bicarbonate. I'll accept both because bicarbonate is just pervasively used outside of chemistry these days. Now, back in the old days, if we did the lead system, we would call that plumus, the Latin root plum, and OUS because it's the lower of the two charges for lead, which could be 2 or 4. So plumus bicarbonate. Back in the day, you know, I'm not going to ask you to do that, but I'm just throwing it on there because it's there and I have the space, right, in case you run into it. So there we go, lead 2 hydrogen carbonate. That's technically the International Union of, why am I saying? IUPAC. I keep saying that stupid thing. Let's go over to this one. Now, we don't have a metal cation, right? But you can recognize in parentheses that that's the ammonium ion, and then that's the phosphate ion. So we have 2 polyatomic ions involved here. So this is the ammonium ion. That's the phosphate anion, right? We got it. Now, what's wonderful about this is actually easier. We don't have to worry about type 2 metals. It's just ammonium and phosphate. So you just go ammonium, phosphate. That's it. You don't alter anything. I love the polyatomic ions. Makes life so nice. So that is ammonium. Right? You do not alter the name of the polyatomic ions ever. Ammonium. It doesn't matter how many you have. And phosphate. Oh, my S was pretty ugly there. Wada bing, wada boom. Not so bad, right, gang? Just the only really tricky part's the type 2 metal. You got to do a little extra thinking there. All right, we'll end this video. In the next one, we'll do covalent compounds, which a lot of other people think is the easiest one. I think it's type 1 ionic compounds. And we'll look at the dreaded acids. No!